We've talked a bit about motion in one spatial dimension and looked at the special case of kinematics, which obtains when the acceleration is constant. To go from one spatial dimension to multiple spatial dimensions, including the three-dimensional world that we happen to inhabit, we need to know how we're going to stitch those spatial dimensions together. And how different spatial dimensions work together. And to do that, we're going to have a little interlude here into the idea of a vector as a mathematical quantity. And we're going to use vectors quite a bit throughout this course, and they're used throughout physics. There are different ways to represent vectors, and there's a few example pictures here. The general flavor for what a vector is trying to do, it's trying to relay to you a quantity that has both a strength and a direction. So we have some colored streamlines in the upper right image depicting how the fluid of the atmosphere is flowing at a particular point in time at different locations in the United States and Mexico and so forth. So streamlines is one way to get this point across. A numerical simulation of a flow past a cylinder as an obstruction. And here we have vectors in the representation, and the strength of the vector is communicated to us through the color, and the direction that the vector points is literally the direction that the head of the arrow is pointing. We can see that you have a complex flow with a vortex after the flow passes the cylinder, and that where the vortex is going to oscillate. Another example, and this is flow of plasma in a cluster of galaxies, where I have vectors, vector field represented as arrows, and the direction that the arrow points is telling you information about what direction the vector field is pointing at that location in space. And the length of the arrow, as well as the color of the arrow, is telling us about how fast that plasma is moving in this particular arrangement. So when we have things that have both a magnitude or a strength and a direction that they point, represent that with a mathematical quantity called a vector. And we'll talk about how we're going to use vectors in this course and what the notation will be in this chapter. And then a little bit about mathematics, about how you do mathematical operations with vectors. The starting point in this, I'm going to go back to a right triangle, our old friend. The coordinates that we're going to use are going to be at least locally orthogonal coordinates always. And so in our coordinate representation, locally at every point in space, you can think of there being a little triad of three mutually perpendicular directions. And then we're going to break our vectors down into those components along those three perpendicular directions. Since those coordinate directions are perpendicular locally, we have right angles. Well, also, it's a flat space, so it's going to be a right angle. All right. As a review, if this angle is 24 degrees in a right triangle, and this side is 4.8, how do I find the length of this side labeled x? So literally find x. So go back into the recesses of your mind and trigonometry and see how to go about solving that. And so you have an answer if possible, confirmed with your physics friends, then proceed on into the video. All right, I'm going to review some things that hopefully are familiar to you. For this right triangle, the side that is opposite to the indicated angle is conveniently called the opposite side. The other side, the one that is adjacent to the indicated angle, is called the adjacent side. And then the odd person out, that is neither opposite nor adjacent, is the hypotenuse. And then our trig functions are ratios of two out of those three quantities, opposite, adjacent, hypotenuse. And how to keep those straight, the way I was taught, was to remember that Oscar had a hold on Arthur, which has reminded me for many years now that sine is opposite over hypotenuse, Oscar had. Cosine is adjacent over hypotenuse, a hold, and tangent is opposite over adjacent on Arthur. This is apparently not the fashionable way to remember what your trig functions are anymore. And arguably, probably the best way is to just remember a unit circle. But what is more familiar now is what sounds as some sort of incantation from Harry Potter. Sakatoa, Sakatoa. Which reminds us that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So, Sakatoa. Apply whatever you want, and let's work out what x is. Let's find x. Well, sine of 24 degrees has to be the ratio of the opposite to the hypotenuse. So x over 4.8 meters has to be the same as sine of 24 degrees. Multiply both sides by 4.8 meters. We have x is 4.8 meters times sine of 24 degrees. So our answer, 1.95 meters. If you did not get 1.95 meters, then check to make sure that your calculator was not in radian modes. This is an angle in degrees. So if you are running a calculator in radian mode, 24 radians is definitely not the same as 24 degrees. So you will have an answer that disagrees with me. So make sure you get that straightened out. All right, let's talk a little bit about the types of mathematical quantities that we're going to be using in this class. There are quantities in physics that are just a value. They're not associated with any sort of direction in space. So I imagine putting a thermometer down in different locations in my office. I'm going to measure the temperature of the air wherever that thermometer is. And so there's no direction that the temperature is pointing. It's just saying that at any location in space, I can go off and investigate what the temperature is at that location at this time. And that gives me a value. And I put those values together, and that's going to give me a scalar field. Okay. It's a field of values. It could vary with time. It's going to vary at locations in my office. But it is just a scalar. It's just a value. There are other quantities that have both a magnitude and a direction that they point. So our kinematics variables, things like velocity, acceleration, as we go into Newton's laws of motion, the things that cause acceleration are forces. Those are all represented as vectors because they have both a strength, how strong the quantity is, and the direction that is acting along, the direction that it points. Okay? So we have things that are just a magnitude. We have things that are a magnitude in a direction. And the magnitude of a vector is itself a scalar. All right. There are other things, the tensors, those exist. We use them to describe lots of different quantities, and they are very useful in physics. But by construction for P221, there is nothing in this course that requires tensors. We're not going to do physics to that level of depth and detail where we would need to know tensors, or if you're a little bit more sophisticated, tensors versus differential forms, and those sorts of things. We can do everything that we want to do in physics at this introductory level without that mathematical complication. And so we won't need tensors. All right, a question for you guys. Read through these 5 scenarios, and which of those scenarios involves a vector, the thing that's being described. You have a tingling in the back of your head, your vector spidey sense goes off, and that is a vector. Right. So read through them carefully, think them through, compare them with your physics friends, and answer which out of those 5 is describing a vector, something that has a magnitude and a direction. And when you have your answer, go ahead in the video. Right, it is only E that is giving us a specific vector. So submarine followed the coastline for 35 kilometers. That is not a direction. And there is no speed. So it's motion for 35 kilometers. So I know the magnitude of the displacement, if I add up all the lengths, it totals 35 kilometers. It's not necessarily a displacement. The coastline is curved. So not a vector. Air temperature in northern Minnesota dropped to -4 degrees Celsius. Not a vector. It's just telling you what the temperature is at a location. Hubble telescope orbits 598 kilometers above the surface of the Earth. Well, there's a mathematical surface. There's a sphere that is 598 kilometers above the surface of the Earth, taking the Earth to be a sphere, but that is not a vector. The baseball flew into the dirt near home plate at 44 meters per second. There's a speed there, and there's sort of a direction, but not really, right? Into the dirt, I could do that at any number of angles, like half of them. half of the angles available to me are going to correspond to going into the dirt. So this is not a vector. It's a vague statement. The one that is a vector, we have a flock of Canadian geese. They are flying due south, so it's a specific direction, at 5 meters per second. I have a magnitude and I have a specific direction. So E is the case that is talking about a vector. I could write out a vector to be the velocity of those Canadian geese.